All right, so where we left off was right about here, where we were talking about other classifications. So, what it would be an example of a fixed sequence robot? Okay, so it does a monotonous task over and over again with no variation, right? So think about a stamping machine. You know what I'm talking about, right? 10-ton press comes down and stamps out pieces of, car, cell phone, what have you. But it's all set up just to do that one thing over and over again. What about a variable sequence? What do y'all think? Variation? Yeah, exactly. So let's say I'll go ahead and tell you this. When I was working automation, we had a company that was wanting to make spoilers for a Honda and door panels for, I can't remember what model car, but these were plastic inserts, and what they use to put them in are these little white plastic clips. But at the same time, they had to uh, use an ultrasonic welder to melt pieces of this together, so that it created a nice strong bond and your door panel didn't fall apart. So we ended up using 5 robots. 4 were welders, 1 was the piece that inserted these clips. But the sequence of it is variable in the fact that I can do a left panel, a right panel, or the spoiler depending upon which run I'm trying to set up. Does it make sense? So it is quite literally a variable sequence, meaning I can do more than one at a time. I can do several at a time. Does that make sense? All right. So when we're talking playback, what kind of a robot would we be talking about? For those, you're talking about the ones that you can actually move through the motion, and it records it almost like a tape recorder records sound. It records each movement and how you're moving it until you get to the final set. And then it's able to play that same run back over and over again. We have some of these that are numerically controlled. What would be a good example of a machine that would be numerically controlled? Mhm. Something like a lathe, or where you might have to be able to program in precise anything to get what you want out of it, like a CNC. A CNC is exactly what that is. All you're putting in are a bunch of numbers, and that tells the arm in there to go to this position, do this, that position, do this, so on and so forth. Another classification is intelligence. Now, I'm not going to go back into the whole spiel, but we all know that robots do not actually have true intelligence. We can make them seem like it, but they don't have it. Right? And then we have the open loop versus closed loop. Open loop is probably some of the most basic robotics. The whole point of open loop is that it does not have feedback from the motors. or from any part of its work cell. Basically, it just goes and does its job day in, day out. Doesn't really get input from anything. We don't have anything to really make it seem intelligent. It just does a automatic job. Versus a closed loop robot, which is what all these are. Those have feedback in the motors, and some of them have sensors enough that they can tell what's going on in the world around them. Sound good? Everybody good? All right, so coming back to this right page, one of the things that we specify is by accuracy. So the definition of accuracy is what? What would be the definition of accuracy? Well, I'm asking more of a, when you hear the word accuracy, what does that really mean to you? Does that make sense? Because yes, you can read that. It's how well can it move that center point. I really don't like how they're saying that. But the whole point of accuracy is that just like anything else, if you can get to the bullseye, you're good, right? With an accuracy specification, what we're trying to determine is how well can that robot go back to that same one point over and over and over and over and over again for its entirety without a whole bunch of overshoots, undershoots, not, is it where it's supposed to be? Does that make sense? Mm-hmm. These robots, some of them can go down to the millimeter, some of them can go down to a micrometer. I mean, they can get that precise. We, as humans, cannot be that precise. We can sit here all day long with a pencil or pen and just pick it up, put it down, pick it up, put it down. A robot will put it down in the exact same spot just about every time. There might be a little variation. So if a robot was doing it and that right there was one spot, the variation for that is going to be maybe just a little bit bigger than that. Okay? Versus a human is going to come down in a lot bigger area. Our area would be about twice to three times as large. Why? What do y'all think? Why would that be clear? Because small variations in the muscle twitching of your arm would move the dot just ever so slightly every time. All right? Because unless you super concentrate on something, it's kind of like how many of y'all can draw a straight line without a ruler? Or cut along a straight line without it being completely perforated? We can't do that because our muscles and the way our muscles run kind of prevents it. Are there ways to do it? Yes. Are there great ways to do it? Not really. All right, so repeatability goes back to accuracy, because not only do we want the robot to be 100% accurate when it's putting a point in, we want it to be able to go back to that one point over and over again for its entire life if we needed to. We want it to be able, if the product does not change and you're using a robot to build that product, and that is the only robot you use for 10 years, if you look at the very first piece it makes to that very last piece it makes, there should not be a very big difference in any part of it. Now you might have a small little piece that's not completely right, but at the same time the robot's repeatability, if it's a great run of repeatability, you won't see a whole lot of oscillation. But eventually the robot does kind of wear itself out over time, so you would see some minor problems, but should not be anything truly major. Payload. Now payload is interesting because I'm going to go ahead and tell you this, and this is something you might want to put in your notes or make sure you memorize in your head. Robots do not come with the tool attached. Companies that make these are not in the tooling business. What that means is that if you have a specified payload, let's say you need a robot able to lift 2 tons. Well, you might want to get a robot that can lift more than 2 tons, because whatever you're having to put as the tool for that robot is going to have to take part of that weight limit. So if you needed to lift, let's say, 500 pounds, your tool weighs, let's say, 100 pounds. Your payload spec needs to be about, let's see, I said 500 pounds. So it needs to be a minimum of 600 pounds of payload. But you don't want to ride that close to the line. You probably would go with 7 plus, just so that you have a robot strong enough to do the job no matter what, even through changes and variation. So the tool is not part of the payload spec. It is something that we attach to the robot. Most of the robotics companies are not into automation. They're strictly building the robot, putting the cabinet together, sending it down the road. These guys don't come with the tool attached. So what we have to do is go to either our own machine shop, if you have one in your office, in your place of work, or you go to somebody that does automation or machining elsewhere. That is a very typical way to deal with that, if you really know the truth. A lot of times companies go to outside sources. The only reason that you might try and encourage them to do an in-house is what? If you design it in-house, it's cheaper and easier to fix. You know how this thing works. You know how to make it do what you want it to do without having major problems. All right? So whenever you're considering a payload specification, okay, that is the maximum weight at which, when placed at a specified distance from the tool plate of the arm, will still permit the robot operation with the specifications of accuracy and repeatability. Because let's face it, we do not want to overload one of these things. What happens if you overload a motor with weight? Huh? You're going to burn it up. And that is actually something that happens if you don't watch the design and make sure you've got the right payload specs. Because that is going to be a problem, and replacing those motors is not something that's easily done. Not to mention, I don't know anybody that wants to take apart one of those robots, especially the big ones. Those are not easy to take apart since you're going to have to remove everything to try and strip it down to where you're having a problem. So one of those things you got to watch is that payload spec and be very aware of what it's doing. Then we also have specification of speed. How fast can it move? Okay? And since the whole purpose of these robots revolves around that tool center point, why does it revolve around the tool center point? What do you think? Why do all our specs seem to run around that same tool center point? It's the area that's going to be working. It's just like your hand. If you have, well, let me rephrase that. If you're trying to do something and you're using your hands to do it, what is the major tool and what do you try and orient and move the most to get what you want? You got to move this, right? You got to move your hand. Same thing for a robot. The whole purpose of the robot is that end of arm tool. Okay? So the speed, payload, and everything else revolve around that tool center point. Just like it does, like our brain revolves everything around your hand. Is your hand in the right orientation? Is it, strong enough to pick up what you're about to pick up? How fast can you move your hand? How many of you like to watch fight movies, like kung fu movies and stuff? All of it's about the what? It's all about the hand speed, right? If you're going to fight somebody, if your hand speed's better, you're the one that's going to win, generally. With a robot, speed is a lot of the times of the essence, especially if you're in production mode, right? What do they do with production these days? You have to have a what? You have to have a specified cycle time. How many of you have heard that word before? Yeah, it's one of those that nobody ever wants to hear. It's the word cycle time. Because that tells you exactly how many pieces they're wanting you to push out in that one time. How fast is this running through its whole process? So speed becomes very prevalent for that particular run because you are trying to keep cycle time down and make sure that you're not either going too quickly and building too many, but you also do not want to be lagging behind and waiting for everything else to catch up. So cycle times are a big thing. Okay? So speed has to deal with the tool center point to a specified place in the workspace with the payload and without excessive over travel or oscillation. Okay? So in other words, it's kind of like your car. If you try and stop it on a dime, will it actually do that without you going over or you having to, hit your brakes hard enough that you rock back and forth for about a minute or two? Range. So I think range is probably something everybody understands really well. How many degrees or how much distance can a joint move? Weight of the robot minus the end of arm tool should be given. That's a basic way to deal with them. Now, why would we worry about how heavy a robot is? Why would we be worried about how heavy that robot is? Say that again? Can the floor support it? Exactly. Put this in perspective for y'all. That is a very big, very heavy machine. If you get that going, he is swinging himself around sometimes quicker than you think. Okay? They can whip themselves around pretty fast. We have certain ways that we have to fasten robots to either something that's connected to the ground or something that is very sturdy. A lot of the times we put them on bases or something like that to help them be able to have a little bit better reach and not have to mess with anything on the floor. But the robot themselves, there are certain ways you have to mount them to either the floor or whatever you're mounting them to, because the last thing you want is that robot tipping over, falling over, or multitude of other things. There are actually concrete anchors, and with that, the other thing comes in that if your concrete is not thick enough to actually support A, the weight of the robot, but B, the robot in motion. Because when something is standing still, but it's got all this motion going on, what can happen to it? It'll fall over. Okay? So you have a vertical reach, that is how high the robot can go when it extends upward from the base. So in other words, how far up can it reach? Just like how far vertically can anybody reach? Your total reach actually goes out to probably the tip of your middle finger, because that is how far you can reach, even when you're on your toes. Horizontal reach is how far out can it reach. Now, why is all that important? Well, that helps also define the workspace of the robot, right? Because just like us, let's say you need a bottle of water that's on the other side of the table. But how many of us are actually going to try and get up and walk to that the first time versus trying to reach for it the first time and trying to just about crawl over the table so you don't have to get up and walk around the table? How many people have done that? Everybody raise your hand, because we've all done it. We all have that lazy moment where we all sit there and go, I don't feel like getting up, but I really want the water bottle. Yes! You get it by the very tip and you're going, okay, now I've got it. Didn't have to get up and walk around. I think we've all done it. Might just be me, but okay. But it's measured from the center of the base to the center of the end of arm tool, and the robot is extended horizontally. So when you're selecting a robot, the very first thing you need to look at is payload. Why? Because if you get the wrong robot that cannot handle the payload that you need it to handle, when you burn those motors out, it's nothing but a giant art sculpture. Does that make sense? Last thing we ever want is an art sculpture that sits there and can't do anything because the motors got burned out. So you need to know what payload you're looking at. How much is the tool going to weigh? How much is the robot able to actually move? What is the product I'm trying to move? If I'm just trying to move a piece of paper with suction grippers, but my grippers have to be giant to move this giant piece of paper, I'm not going to need an extremely high payload spec for my product, but in order to get the suction cups to stick and hold, I might need some heavy equipment to make it do that well enough to actually keep hold of that flat surface, especially if there's any dirt on said flat surface, right? So that's a lot of what you have to consider with this. Degrees of freedom. What did we say that was? What is a degree of freedom? I'm thinking nobody drank their caffeine this morning. Is each axis. The degrees of freedom are each joint and or other term being axis. In other words, that's where it either moves straight or it moves in a circle, but it is every individual joint. So when you're considering it as far as degrees of freedom or joints, if you want to call it that, that's to do with expense. Because the more joints a robot has, you have one of two problems that can occur. A, the more joints you have, the more expensive the robot's going to be. And that's just an ultimate truth, guys. The more joints something has, the more complex it is to build and program, the more it's going to cost. Number two, the more things you add to anything, the more likely something is to what? More likely it is to break. So you only want what you need. You do not want a 6-axis robot whenever a 4 or 5 will do instead. If you're just having something come over, pick something up, and move it, it's up to you to determine, do you need a true 6-axis robot to make all these micro moves, or can you just make it move to pick things up and move it? Drive power, 99% of that should be electric. Now, if you're talking about the tool itself, then you're getting into hydraulics and pneumatics. Most drive power for the machines themselves is electric. Okay? You will find electrical components on just about, well, I wouldn't say, no, just about every robot has its own electrical something. Even if your tool is, and even if the robot runs completely on pneumatics, the tool is pneumatic, you still have to have an electric compressor to make pneumatics work. Does that make sense? Repeatability, we've talked about. How well can it repeat the task over and over again? Accuracy, how well can it go back to that specified point? The workspace dimensions is one of the big ones we do, because you are taking something and mounting it to the floor, or at different scenario would be to mount it on a track that can move left to right, or up and down, if you will. That would be a 7th axis. But the whole point I'm trying to get on that one is that you still have the robot itself bolted to something. The robot cannot be like a human being where, oh, I need something that's across the room, I need to stand up, walk over, and get it. Instead, the robot's going, okay, well, you might want to install a conveyor belt, bring that to me because I cannot move to it. That's why you need to know the work dimensions, because the robot can't get up and walk off. It's kind of permanently bolted to the floor. If it can do some moves like that, it's not for very far. It's not like it can move around the whole factory to get where it needs to be. Put it that way. Speed, how fast does it go? It says again, you're dealing with things like cycle time in most businesses. If you've ever had to deal with cycle time, I always wonder who comes up with those cycle times, thinking that that's how it needs to be done, but cycle times are the norm in industry. How fast does this need to be made? How fast can we make it without default defects? Memory capacity, just like a computer, the more memory you have in a computer, the more it what? Hmm? Have any of y'all looked at computer prices before we had the computer chip crisis? All right, so the more memory you asked for in that computer, the more what? The more it costs. The more memory you have, the more it's going to cost you. Programming support. How well does the program work? End of arm tooling. Now, again, automation companies are going to have to be where you look for that, and or your own machine shop. But that has got to be something you consider whenever you're trying to determine what job this robot's going to do, as well as what size you need it to be. And then environmental requirements. So, how many of you ever kind of watch how it's made? That's one of the really great shows out there, right? How are things put together? How are they created from raw material to the goods that you buy, right? So if you have, let's say, a robot that uses a paint sprayer, that would be a very specific environmental requirement. What would we have to do to protect the robot and its joints from that environment? And I will say this is actually something that's done quite frequently. Do we just leave the robot standing there in the paint booth? No, we generally put covering of some sort all over the robot, because why? Because we don't want paint buildup getting into the joints, right? That would pretty much be disastrous for the robot. Because the more paint you put there, the more it's going to end up blocked up where it can't move. And then you have a fancy paperweight that just kind of sits around and you can't do nothing with it. Right? So degrees of freedom, we've already called it the axes. If the end of arm tool is integrated into the robot, it can be part of that. But like I said, most of the time you will not have a tool that is sent by the manufacturer. I don't care if you go to KUKA, Motoman, any of them. They generally will not send you a tool that is part of your robot. Now, if your robot is a simpler machine type robot, not one of these, then maybe it has a very rudimentary gripper or rudimentary drill that you could always take off and replace. Okay? The degrees of freedom on a robot are rarely less than 3 degrees of freedom, or 3 axes. And there are very few that are, well, I won't say there are not more than 6. There's a lot of robots these days where we've decided that we want to have them be more mobile. What does that mean for us? It means that because we're putting them on something like a track that allows them to move in a different plane, there can be a seventh axis for these robots. Because we can mount them to a gantry, or we can just simply mount them to a track that has them running one way, back and forth, all day long. So I won't say it's rare that it's greater than 6 anymore. It's actually becoming a bit more common these days. But we generally do like to have these guys bolted to the floor. It's a lot more stable and a lot less chance of the robot tipping over. Because if you ever really look at the robot, it does not have a truly giant heavy base. The top part of it probably weighs about as much as the bottom part of it. We don't want them tipping over. So this is a robot on a transverse base. So this is it. The robot itself is this guy, and then he's able to move back and forth on this base. Now, one of the cooler robots is this guy. He's what's called a Delta robot. And he moves very interestingly. I've got some video I can let y'all see of it. This one's a mobile robot. It looks like it might be a, I'm not sure what they set that one up for. Those look like video cameras. You have aerial robots, aka what? They're drones. They're flown remotely or they're pre-programmed to do what they've got to do. You have marine robots. Now, why would a marine robot be a big thing? Something that we like to have. See what's underwater. There's only so far humans can dive, even in a submarine, before the pressure tends to collapse a lot of things. Y'all hear the chirping too, right? Okay. I think that might be somebody's phone or something. Okay. ADHD moment, sorry. Marine robots are great for exploring underwater because A, you can send it under and leave it under for hours at a time without having to have oxygen tanks. They're great for exploration. They can go down further than we can, and they can stay down longer than we can. What's the disadvantage of something like that? What you can actually capture as far as video of something. Because you have, it's not you that has the ability to turn your head and look around you, turn your whole body around you. You have a very focused lens that you're trying to maneuver so you can get the best pictures and the best video of what you see down there. So it does have its limitations in what can it actually see whenever you've got it under. Okay? So they're great for some things, not so great in others. But that's pretty much anything you have. So drive power source, method used to power all the axes of the robot. Drive will be one or more of the following. Electric motors. Again, electric motors are probably the most common thing with robots. If you look at any of these right here, those, all of these run on electricity. They do not run on air. However, the tools that you add to them are generally run by hydraulics, pneumatics. Some of them are electric. Depends on the job you're trying to do and how much you want it to do that. So going back to repeatability, this is one of the most important specifications of the robot. How many variations will occur on repeated turns to a manually taught point when the taught program is executed? It is calculated for the worst case conditions with maximum payload and full extension. So in other words, it's calculated that, let's say I've got a 5-pound weight on my wrist. Okay? That's the maximum payload I'm currently capable of whenever I'm moving my arm. Is that 5-pound payload? What I'm looking for as far as repeatability is that while I'm holding that payload, can I come back to the same point every time. Humans, not very well. Robots tend to be a little bit better about it. That make sense? Accuracy is normally not specified, but is the smallest adjusting movement the tool center point can make in order to reach an exact point in response to a command. It may also be called resolution. So in other words, how well can you line up your tool with this one specific point you've got to get it to? Because just about every time you look at anything that's made, there is a very specified point that it had to go to get that part made. So let's say a car roof. You have to weld the car roof onto the car. Now initially it's all spot welds, right? You don't have the robot actually engage a full welder. You have it spot welding. Well, how do they determine where they're going to spot weld first? Anybody know? What is the quality supposed to look like? Okay. When you're looking at accuracy, it's a lot about here's the car, here's where I need these to be spot welded to hold this roof steady so somebody else can come back and weld behind it. Right? And you want to have those in very specific places because if it's too far in, it's not going to weld anything. It's just going to be a giant spot that looks halfway welded. It won't hold the weight and other things. So accuracy is one of the biggest things we can do with these robots. It's a great thing about them. Workspace dimensions. So basically, what is your workspace with this robot? What is your workspace as a human? If your chair is bolted to the floor and all you have is your ability to reach with your arms and your fingertips, how big is your workspace? Okay? So here's one where they're talking about the workspace, how big a stroke it can move. It's got its function, the description, how fast and what kind of motion it can move, and what the axis is driven by. And here's one that's an actual drawing. What they're showing you here is what is the vertical reach, okay, and the horizontal reach. So how far out can this guy extend? How far up can he extend? Because let's say I want to put some bins up here for him to work with. So he has to reach all the way up here, pick out parts from a bin, and then this is its main workspace, and let's say there's pieces that it pulls off that workspace and puts on the floor as like a trash heap. That would be a great thing to know, right? All right. All right, so speed specifications. So speed is all about how fast can we get that tool center point where we need it to be, right? And speed is of the essence a lot of times because it goes back to that, how many cycles are in a day? How much cycle time are we wasting trying to get something to go through? It can be given either in English or metric. A lot of it will generally be metric. Why? I don't think that's probably the best way I can say that. Metric is used because all but I think a handful of countries now use only metric. 90% of the world minimum. I think we are one of like 3 countries that are still, or 3 or 4 countries that are still holdouts. on the English system. Everybody else went to metric. Why? Because it's all based on multiples and powers of 10. So most of it is given by metric. They do have English conversions, but metric is the preferred and usually the default. You also have to remember that the people that manufacture all these, generally not made here in America, or not started in America. There are a few of them that run here, but for the most part, they don't. Memory capacity. This is the length of the program, or the number of points that can be used. Okay. Just like your computer can only store so many programs. I've said it before, I'll say it again. These are nothing but giant computers attached to something that can make commands into reality. Okay? The computers that control a robot can make it move in a reality-based way. Does that make sense? Or is that only making sense in my head? Okay, so there's two different ways a robot can be trained. One is called the continuous path. In other words, it records every move you make as you make it, so you're literally walking it through all the steps you want it to do. Lots of robots, however, also run what is called point-to-point. So in other words, if you have, let's say, let's go back to welding. If you are just basic spot welding, one of the things you do is you can say, I want you to put a weld here, a weld here, a weld here, and you can put as many welds as you want to with that robot. And it records each of those points and says, okay, so this is where you go for this is where I need to go for this is the program I'm running. So that's a point-to-point. That's actually what all four of these are. All five, rather. So continuous path robot. It's a good picture of one. I think I have a video of it somewhere. I'll have to pull it up. Programming support, the measure and availability and quality of the programs for the machine. In other words, how well do the programs actually run it? We have what's called the programming languages, because each of these is different. Okay? Oh, we're not talking like, when we're talking program language, each robot programs exactly the same way. You have X, Y, and Z axes. You have same joints. Nothing really changes from robot to robot. Just like a cell phone. Does it really matter what cell phone brand you get? All the operating systems, basically all the phones work exactly the same. What's the difference between them? Let's say an Apple versus an Android. It's the operating systems, yeah. All you have different are the operating systems. So it's still a phone, still calls people, still plays messages, you can text, you can play games on it, you can do all that. All that changes is maybe the way it's set up to do those tasks. Does that make sense? So the same thing goes for each robot. They all program the same. They all do the same thing. What it takes that's different is the different language. ABB talks to the computer in Rapid, Bannock in Corel, Kuka KRL, Malfa Basic for the Mitsubishi that's in there, and the Motoman does the Inform 2. I will tell you now, they don't really change this much. If you look at the teach pendants we've got in here and the ones from, say, a brand new Fanic or a brand new any of one of these, it's the same teach pendant. Most of them have just been upgraded to things like touchscreen, but they're all the same teach pendants. Okay. End of arm tool. Most robot manufacturers are not in the tooling business, so it isn't fabricated by your end user. Or companies that specialize in that end of arm tool. Most robots are designed to operate under typical factory conditions. What does that mean? What would be a typical factory condition? You're dealing with temperature, you're dealing with particulate that's in the air, things like that. You know, temperature controlled, generally dirt and dust free, things like that. But provisions must be made to keep the electronics cool. Now that is actually a really big thing, because what you'll kind of see whenever you're over there, the robots tend to put out a lot of heat in the control box. Why? Well, that's because it's a giant computer. If you have ever set a laptop in your lap, how hot does it get? It gets pretty hot, right? Same thing for the controllers. So we have to keep them cool. But at the same time, we don't want a lot of dirt and crud in them, so we also seal them up pretty tightly, just like a computer. You have ways to draw air across the electronics, especially the ones that are most vulnerable, but you have less ability to get dirt and stuff in there by sealing them up tight. Okay, and that was the last slide for that. Okay, y'all got any questions on anything we went over the last couple days? Okay.